In this video, we will be solving this system of linear equation using the Cramer's rule. Of course, in our previous videos, we had solved this same problem using matrix inversion method, substitution method, elimination method, as well as Gaussian elimination method. Alright, so this time around, we are going to use Cramer's rule to solve the same system of linear equation we have been working on. Earlier, this system of linear equation had been solved using matrix inversion method. It had been solved using substitution method, elimination method, as well as Gaussian elimination method. So this time around, we'll be using Cramer's rule. Now, you know the idea in the use of Cramer's rule in solving linear equation is transforming it into a matrix form of the form in the form AX equals B, and such that the solution to each variable appears in this form. Okay, let me not confuse you with this. Let's just go straight into solving the problem. Let's transform on the first step. Let's write the system of linear equation in the form AX equals B and compute the determinant of A. So A becomes the coefficients of each of the variables. So the elements in A, for example, the coefficients of variable X is 1, 2, and 3. You can see 1, 2, and 3. The coefficients of variable Y is 1, minus 1, and 4, 1, minus 1, and 4. The coefficients of variable Z is 1, 3, and minus 1, 1, 3, and minus 1. Of course, for the variable elements, the three variables we've got are X, Y, Z, and the elements, the constant values are represented by this vector B, 6, 14, and 1. 6, 14, and 1. Now, it is important to also, because that is what Cramer's rule is all about. So what Cramer's rule states, what we are trying to describe here basically, is that you see this is the matrix A, the main matrix component of the system of linear equation. So we then can find AX. And what is the difference between matrix A and matrix AX in this context? You will find out that for AX, the coefficients of X here, the elements that represent the coefficients of X have been replaced by the constant values 6, 14, and 1. So what will then also be the matrix AY will be that the coefficients, the element representing the coefficients of Y would simply be replaced by the constant values 16, 14, and 1. And of course, every other thing will remain as it is in the main matrix form of the system of linear equation. So you see, only the elements represented by the coefficients of X was replaced by the true values in AX, and for AY, only the elements that represents the coefficients of Y have been replaced by the true constants. The constant values So, and for AZ, look at this. These are the same, these are the same, but the elements that represents the coefficients of the Z have been replaced by the constant value 4, 6, 14, and 1. So this is your AX, this is your AY, and this is your AZ. Now, Cramer's rule states that the value or the solution of to variable x will be equal to the determinant of AX all over the determinant of A. The solution to variable y will be the determinant of AY all over the determinant of A. And also, the solution to variable z will be the determinant of AZ all over the determinant of A. So we said the first step is to write a system of linear equation in this form and compute the determinant. So let's go ahead and compute the determinant of A. So computation of the determinant shows that we've got 1, 1, 1, 1. Of course, you alternate the sign, 1 minus 1 and 1, and you have the minor matrices, and you get the determinant of the minors, and well, playing around with that equation to determine the determinant of, to compute the determinant of A, shows that the determinant of A gives 11. So just play around with that matrix A to compute the determinant, and you will see that the answer is 11. Now, the next step is to compute the determinants of matrices AX, AY, and AZ. So for matrix AX, we want to replace the first column with the constant value 6, 14, and 1, and that we've done here. That is Cramer's rule. So we then find the determinant of AX, and we also play around with this AX matrix to find the determinant to get, and if done appropriately, the value, the answer gives 8. We then move ahead to get the to work on matrix AY. The matrix AY is, well, gotten from matrix A by replacing the second column with the constant values 6, 14, and 1, and that we've done here. So we also find the determinant of AY, and that gives us 9. Right then, so moving on from there, we also get matrix AZ by replacing the third column with the constants 6, 14, and 1, and that we've done here. So we then move ahead to compute the determinant of AZ. So, and that we've done here, working on the minors, the determinant of the minors, and playing around matrix AZ to compute the determinant of AZ, shows that the determinant of AZ gives 46. So what we then do using Cramer's rule is to divide the determinant of AX by the determinant of A to get variable X, and that gives us 8 all over 11. And we also use the Cramer's rule to divide, to say determinant of AY all over determinant of A, and to get Z, the determinant of AZ minus the determinant of A. So doing that shows that variable X becomes 8 all over 11, variable Y becomes Y all over 11, 9 all over 11, and variable Z gives us 49 all over 11. So you can compare this answer to using other methods of solving systems of linear equation and see that the answers are all the same.